In this video, I cover studies on combining local resources and living organisms into habitat structures. While this video will mostly cover a NASA-funded project, including a proposal that plans to run experiments on the upcoming Starlab space station, first I want to briefly cover a Chinese proposal that I came across recently. The study proposes using microbes in building or growing habitats off-world. Microbes aren't limited to construction. They could, for instance, be used for biomining, that is, extracting valuable metals from asteroids far more efficiently than conventional methods. From this graphic from a study carried out by the School of Civil and Hydraulic Engineering in China, you can get an overview of their design. The link to the study is in the video description. While the study considers the Moon and Mars, due to the lack of carbon availability on the Moon, I will focus specifically on Mars, which has an atmosphere made up of over 95% carbon dioxide. As an aside, for the Moon, humans breathing out carbon dioxide plus waste products that contain carbon could be used to produce biostructures, but this technology makes the most sense for Mars, which is why it's the focus of this video. Let's look at the two main ways to create biostructures. Biostructures, Mycelium Composites and Biocement. The Chinese consider both methods, while the NASA study is more focused on using mycelium to grow structures. Mycelium Composites, Fungi-Based. NASA's Mycotecture Off Planet project, which I'll explain in more depth later on, proposes using mycelium-based composites for growing structures. Mycelium, which is a thread-like network formed by fungi, acts as a natural binder. It could be fed by mission-generated organics, such as inedible plant parts or bio-waste. The fungi require substrate, which would be Martian soil, plus an organic feedstock or nutrient supplement. The regolith acts as a bulk filler, which is bound together by the mycelium that weaves itself through the regolith and binds to it. The end result is a stronger material, providing more insulation, flexibility than regolith alone. It's possible to make domes or bricks using this method. This organic material doesn't outgas as much as synthetic materials, which is a problem in a confined space such as a Martian habitat. After growth, the composite is baked or dried to stop further fungal activity and create a stable structure. Biocements, bacteria-based. Biocements, often produced via microbially induced calcium carbonate precipitation, or MICP, use bacteria to precipitate calcium carbonate minerals that bind particles together, similar to natural concrete. For use off-world, bacteria would metabolize compounds, such as urea, to create binders. These bind Martian soil into bricks or other structures. For even better results, combine with extremophiles, like cyanobacteria for oxygen production, radiation protection, and enhanced binding in harsh conditions. For Mars, which is heavily contaminated with perchlorates, adding bacteria like Azospira, oryzae, would break down the perchlorates into chlorine and oxygen, which is a resource, plus detoxified regolith. Bacteria can be used to either extract valuable materials and metals from regolith or to remove toxins, with the possible side effects of realizing valuable resources such as oxygen and clean regolith for construction. You can imagine a two-stage process of treating the regolith with bacteria first, and then using the fungi to bind and grow structures. Benefits of biostructures. Probably the biggest benefit is very little material needs to be shipped from Earth. From the Phase II final report from NIAC, we can see that a melanin-rich fungal and hydrogel combination requires transit of less than 1% of the final mass, because 99% can be derived from in situ resources. That is, Martian soil provides nearly all the mass needed for base and infrastructure construction. Extremophilic microbes, tough bacteria, that not only survive but thrive in extreme conditions such as high radiation, low pressure or temperature environments. Imagine growing a permanent base on Mars using only small amounts of imported microbes, carefully selected to thrive under Martian conditions. Roadmap as proposed by the Chinese study. The Chinese study breaks the problem down into 4 stages. First, send hardy microbes to space to break down toxic elements or gases to make environments livable for humans. Second, use the microbes to process local resources. Third, mix local materials into microbe-made binders to create bricks or structures. An example would be bioconcrete for use in construction. And fourth, integrate the microbes into life support systems. This creates a closed-loop system to process biological waste or trace gases into useful or benign substances. Key challenges of microbe-based structures and materials. Microbes die if the environment becomes too extreme. Think high radiation, low gravity, extreme temperature swings, or toxic compounds present. In addition, it can be challenging and slow to pick the best strains to breed. More testing in space is needed. Commercial space stations should solve this problem, which is why it's important they are funded soon and at the right level to become profitable. Another challenge is it's uncertain how well these biomaterials would hold up over time. Let's now turn our attention to NASA's research into the area of growing structures rather than building them. Myco-Architecture, growing a Martian base camp. The NASA proposal, funded by NIAC, the Innovative Advanced Concepts Program, is run from NASA's Ames Research Center with Dr. Lynn Rothschild as a principal investigator. The team received Phase I funding in 2018, progressing onto Phase II funding in 2021, and in 2024 received a Phase III grant worth over $2 million. The idea is to send dormant fungi off-world, the Moon, Mars, or beyond, and have the mycelium grow into custom shapes, such as bricks, panels, or perhaps even entire structures. You can even grow furniture, such as chairs or tables. As stated earlier, these biostructures are fire-resistant and lightweight. This approach could dramatically cut the amount of mass needed to be sent off-world, especially to Mars. Certain strains of fungi naturally absorb radiation, such as the melanin-rich black fungi found at Chernobyl, so it helps alleviate radiation exposure that a Martian base would be exposed to. As I've stated in a previous video, I believe the dangers of chronic low-level radiation are overstated, but less radiation is always better. Mycelium-derived materials are already available commercially on Earth. Their compression strength is superior to lumber and with greater strength than reinforced concrete. In the presence of food, sunlight, and water, mycelium structures can grow or repair themselves. Additional structures can be grown by providing mission-produced organic waste streams. The more tourists and astronauts at the base, the more structures you can grow. Once a structure is no longer needed or has become degraded, it could be broken down to provide fertilizer for farming at the base. Alignment with NASA's Mars plans. Using mycelium structures aligns with NASA's Mars Design Reference Architecture 5.0, specifically the surface mission strategy known as commuter scenario. Let's unpack that statement, which contains a lot of jargon, so we fully understand what the study team means. First of all, let's explain NASA's goal for Mars. There is a 2009 NASA study on planning human missions to Mars called Design Reference Architecture 5.0, commonly shortened to DRA 5.0. It's not so much a program or schedule, but more of a blueprint. It proposes long stays of 500 to 550 days, with 6-month transits each way. Cargo would be pre-deployed, propellant would be manufactured from local resources, and nuclear is baseline, not only for the base, but also for transportation, specifically nuclear thermal propulsion, although I guess nuclear electric propulsion would also be considered. Now let's explain the commuter option. This strategy for Mars exploration uses a centrally located monolithic habitat landed in a flat, safe area. This is home base and consists of the primary living structures and lab for the entire surface stay. 2 small pressurized rovers are used for crewed day trips, typically 100 kilometers or less round-trip range, with crews returning to the main hab at the end of the day or excursion. 2 unpressurized rovers would be used for cargo or for light mobility. Power would come from a surface fission reactor that would be pre-deployed on the surface. Exploration would take place by commute, hence the commuter name, from the fixed hab to interesting sites, for instance nearby craters or outcrops. So, now let's look at how the Myco-Architecture would fit into this scenario for Mars exploration. Instead of pre-built and heavy mass needed for traditional habitats, The team proposes sending lightweight, dormant mycelium with feedstock in a compact form. On Earth, a flexible plastic shell produced to the final habitat dimensions would be seeded with mycelia and dried feedstock added to the outside, which would be sterilized. On the Martian surface, crew would activate the structure by using locally sourced water and heat the structure to start the growth process. This approach replaces the heavy central hub structure shipped from Earth as envisioned by the commuter strategy. Instead, less than 1% of the mass would be required, with the rest of the mass coming from the in situ derived mass. This slashes launch mass while enabling self-assembly, radiation protection, and self-repair, enabling a more sustainable approach to base construction. The team proposes using the future Starlab space station for testing the growth of the fungi under microgravity conditions. One of the challenges is picking the best strain, which requires a lot of testing. That's why future commercial space stations like Starlab Space are vital. Unlike the Chinese study, the NASA research is focused on fungi. Both studies have the same goal of growing structures that are lightweight and multifunctional, making full use of local resources. Final thoughts. Thinking about it, microbes and fungi are complementary. Use microbes to handle initial resource extraction, and then use the fungi for actual habitation construction. Both of these approaches could lead to a much more sustainable approach to off-world resource harvesting and infrastructure construction. If successful in developing a biocomposite material that can grow itself, NASA will have a radically new, cheaper, faster, lighter material for designing habitats for extended duration lunar missions, Mars missions, and mobile habitats, as well as furniture and other structures. With Phase 3 funding, the team is prepping for future real-world testing with demonstration missions on Starlab, a commercial space station that's due to launch into orbit in 2029. They plan to grow interior panels, furniture, such as beds and chairs, or small test structures to evaluate strength. The idea is to optimize properties such as radiation shielding. Early studies showed a 99% reduction in proton radiation with just 3 inches of material. The vast majority of galactic cosmic radiation is caused by protons, so a 3-inch thick habitat could cut radiation exposure on Mars by 90%. What do you think of the idea of growing structures or entire habitats from fungi? What about the use of bacteria-based biocement for extracting valuable materials using bacteria? Leave your thoughts and opinions in the comments section below. Thanks for watching. If you enjoyed this space video, consider buying me a coffee to help fund more episodes like this. The link is in the description. Space News Live is on Saturday evening or Sunday morning, depending where you watch from. The live stream is a great way for you to share your thoughts and opinions on the videos I posted this week, or on any space topic in general. I highlight the most thought-provoking comments on videos I've received, along with previews of upcoming content. If you got the time, please tune in and say hi. Be sure to like and subscribe so you'll see our upcoming videos. We make videos every week covering the space industry, with an emphasis on the smaller space startups that aren't covered so well on other channels. See you soon.